Okay, we are ready to roll. So welcome everyone. Hope you're all doing okay. Things are starting to get busy with this course. As you've noticed, we'll now have weekly labs. And a reminder that the midterm exam will be held on, forgot the exact date, week 7, Monday. Yeah, 12th of July, right? So it's not too far off. And everything that we're essentially covering since week 1 is going to be on the exam. I'll talk a little more about the midterm as we move forward, and I'll also give you a sample exam to test out. But just a heads up, keep that in your mind, right? That we do have a exam coming up. Now, yesterday was, of course, our public holiday, so we couldn't have a live lecture. However, what I've done is I've pre-recorded content, essentially the first half of this slide set, which covers, I mean, ideally I would have covered DNS first and then covered P2P, CDNs and socket programming. But I thought DNS is a rather important topic, and hence I should do it in a live lecture, give you a chance to ask any questions. So I kind of flipped a little bit. So I covered all of this in the pre-recorded video. So it will talk about P2P, just the basics of P2P, contrasting it with client server, talking about BitTorrent, talking about distributed hash tables, then going into a little bit of video streaming concepts and CDNs, and a brief discussion on socket programming. More, of course, this discussion was rather generic because given that we support 3 programming languages, I can't really go deep into any programming language stuff, but I did go over some of the general concepts which should help you start writing your own programs. And in fact, in the lab this week, lab 2, you will be writing a very simple socket program. So that should hopefully be exciting for you. So what we'll do today is entirely focus on DNS. So this entire lecture will be on DNS. If there's time left at the end, I'm happy to take questions on any of this content that was covered in the recorded lecture, because you didn't get a chance to ask me live questions then. Okay, so hopefully that's all okay with you. All right, so what is DNS? Now, before we get into DNS, I mean, in the context of, not necessarily in the context of networks, but we as individuals, right, we have all sorts of identifiers. So of course we have our name, that official name. You might even have a nickname that your friends call you, friends and family call you with. At uni, you have a ZID, you have a tax file number, you're paying taxes, you have a passport number. So there's a number, various identifiers, which have specific purposes for various systems, right? And of course, we use them in the correct context, right? So when you, for example, when you meet someone at uni, you don't introduce yourself saying, hey, I'm ZID XYZ, right? You say, okay, hi, my name is so-and-so, I'm a CSE student or whatever, right? Now, similarly, on the internet, if you look at the most devices that are connected to the internet, all of them have IP addresses. Now we'll talk about IP addresses at a lot more length later in this course, but a very brief overview. So IP addresses are 32 bits. They're separated into, so essentially 4 bytes. So they're separated into 4 1-byte blocks. And then each block is represented as a decimal, right? So you might see IP addresses like, I don't know, 128.54.33.254 or whatever, right? So that's essentially an IP address. Each device connected to the internet has to have a unique IP address. Note that these IP addresses, the way they're assigned, there's actually some logic to that. So they're sort of hierarchical, and we'll talk about all of this in much more detail when we cover the network layer. So we'll sort of defer that discussion for now, and you don't really need to know all that nitty-gritty right now. All you need to know is, okay, there's this unique identifier that each device connected to the internet has. Now, in addition, many of these devices will also have what's essentially a mnemonic, right? So a name that we humans can refer to them by, right? And this is particularly very common with any website you visit, right? So for example, you go to yahoo.com or google.com or netflix.com, whatever, right? So that's the name that we remember. Now, of course, in reality, google.com is perhaps hosted on a certain server, which has a particular IP address. Now, we as end users, it would be really bizarre if we had to remember IP addresses, right? I mean, that would be impossible. I mean, imagine not using names like this and having to remember IP addresses. That just wouldn't work, right? Because we humans, we are better at remembering these sort of names. At the same time, if you consider routers, right? Routers, what do routers do? They are responsible for forwarding your packets, and they need to do this as fast as possible. So for routers, it's actually much easier to have this sort of fixed 32-bit value, which they can quickly look up, right? Rather than sort of trying to match up these very long names, right? Alphanumeric names. So for routers, it's better to have IP addresses when they are looking inside packets to decide where to get to. But as humans, we need to remember this, right? So clearly there's a need to map one to the other, right? And that is precisely what DNS does. So if you think about it, DNS is sort of like the yellow pages or the white pages, as you may remember, of the internet. It allows you to query the system. So you can ask, hey, what is the IP address of yahoo.com? And DNS will spit it out for you. And you can also do the reverse. So you could say, hey, what is the host name for x.y.z. whatever, right? And DNS will respond back with the host name. So it's essentially a mapping service, right? Now, itself, if you look at DNS, there are two components really. One is the distributed database that's managing this. So this is essentially, how do we store that yellow pages, right? So do we store that entire big fat yellow pages of the internet in one server, or do we distribute it across multiple servers? Now, hopefully you already have guessed that this would not work in a centralized setting. So the actual database is distributed and maintained across various servers. And these servers are typically called name servers because that's what they're doing. They're mapping names, right? So DNS servers are often referred to as name servers. Now, besides that, DNS also defines the actual application layer protocol that is used by these name servers and the end hosts to communicate with each other, right? So for example, on your machine, when you open a browser and type whatever, say yahoo.com, that will generate a DNS query to this DNS black box, and the DNS black box will eventually spit out the response, right? So the application, the DNS protocol itself defines the format of these messages, the actions to be taken and all that, as we've discussed with any application layer product. Now think about it. If you think of this mapping, right, this is a very fundamental thing for the internet. I mean, DNS is extremely important for the internet. And I'll talk a little bit later how a lot of attacks target DNS, because it's if you can bring down some aspects of the DNS ecosystem, that will cripple the internet. And there have been several instances of this happening all throughout. It still happens from time to time, okay? So DNS is really extremely fundamental. Virtually any application requires to use DNS, because any application particular where, remember, all applications are catered for users, right? And as users, we will always use these sort of names. So almost every application out there needs to map these names to their IP addresses, to the actual IP addresses of the servers hosting those applications. So invariably, every application needs to use DNS. So it's a very fundamental and core internet function. But if you think of how it is actually implemented, right? So remember, these name servers that are part of the DNS ecosystem, they're still sitting at the edge of the internet, right? So just like web servers, we talked about how web servers sit at the edge of the internet, or mail servers sit at the edge of the internet. Similarly, DNS servers also sit at the edge of the internet, right? So they're not part of the core, right? Because the core is just the routers, right? So this has been a very fundamental design principle of the internet, that we want to keep the core as simple as possible and push all the complexity to the edge of the internet. And the design of DNS precisely reflects that, as you'll see, that the entire mechanism, the entire DNS ecosystem is implemented at the edge. The routers don't care. I mean, they're not really playing any role, specific role. They're just forwarding DNS packets, just like they forward web packets, just like they forward email packets. Right? So there's a question, does the edge represent end systems? Yes. So the edge represents all the end systems, or the hosts as we call them, right? So these DNS servers are end systems, just like any other server, really. Okay, so a bit of history, going back to the 70s, when the internet sort of first came about, all these mappings, the host name and IP address mappings, were actually placed in a local file called hosts.txt within the operating system in that particular folder that you see here. And all of this was actually maintained by the Stanford Research Institute, which was one of the key players at that time in designing the internet. And specifically, there was this one individual called John Postel, who was essentially Mr. DNS, right? So he was actually singularly responsible for these hosts.txt files. So anytime you wanted to, in those days, anytime you wanted to set up a domain, you used to actually pick up the phone, call John Postel and say, hey, I want to set up this domain. This is my IP address. And then John Postel would add it into the host.txt master file. And then all the other devices connected to the internet would go and periodically obtain the latest copy of the hosts.txt file from the Stanford Research Institute, right? So this is how DNS used to work. And in those days, it worked okay initially because there were only a few domains, right? The web wasn't even there in the 70s. I should also slightly digress and say John Postel is actually one of a key figures in the internet history. So he's actually he's a co-author on over 200 RFCs. So he's done a lot essentially for the internet. Okay, but in any case, so this, as you may realize, was not scalable, right? I mean, imagine doing this today. This just wouldn't make sense at all. So as the internet started growing, this created lots of problems. There was just too much load on poor John on the SRI. There were issues with naming systems not being unique because pretty much anyone could choose their name. John wasn't really responsible for checking if this domain was already taken, right? So you could have two individuals pick the same domain, and that would create all sorts of problems. There were some inaccuracies with essentially maybe some hosts were not pulling the hosts.txt file in time and so on and so forth. And in fact, there's an incident way back when John Postel actually, you can read up a little bit more. I forget the specifics, but he basically, I think he uploaded the wrong host.txt file into some servers, and that pretty much brought the internet to a standstill. So in any case, this was not scalable. So then the people sort of running the internet said, hey, we need something better. We can't have one individual do this. And that has led to the DNS system as we know it, right? So what does DNS provide? Let's briefly look at this. We'll kind of dissect all of this in a lot more detail in the rest of the slides. As you see, the entire lecture is on DNS, right? So we are going to go into a lot more depth here. But just to give you a brief understanding of what DNS does. So of course, the first fundamental thing DNS does it allows you to map a host name to an IP address, which I've already kind of hinted, right? So you want to visit google.com, your browser sends out a query, and then into the DNS ecosystem, which we'll of course discuss, but eventually you'll get back an answer saying, hey, google.com is hosted at IP address x.y.w.z, right? So that's the first fundamental service. And by doing this, essentially you're keeping the host name and IP address in a way independent. So that essentially allows you to do indirection, right? Because what this means is, if Google wanted to, they could easily replace their web server, right? So they could say, hey, x.w, whatever, that particular server broke down. Let's now host the web server on a.b.c.d. And that's perfectly fine. All Google now needs to do is change the DNS record, that this mapping, and everything works, right? So this indirection that DNS provides is extremely useful because the user-facing stuff, which is essentially the host name, can essentially remain the same, and then the IP addresses can change as required, right? So for example, initially you may set up a web server that you might manage yourself. If you realize, okay, this is too much, I need to scale up, you could just offload your content distribution to a CDN service like Akamai or Cloudflare or whatever. And all that you need to do is make some simple changes to your DNS records, and that takes care of everything, right? So this indirection that DNS provides is extremely valuable, as you'll see. The third thing noted there is what's referred to as host aliasing. I'll show you some examples, but essentially what this means is almost always, right? So if you're saying I want to access google.com, now the actual name for the server that Google is hosting its web server is not going to be www.google.com. It's very likely going to be some longer form name, because internally, right, within the Google's network, they need to assign unique names to all the systems that are publicly addressable. And clearly they can't just have a web server with the google.com name. You'll probably see much longer names. And I think there's some examples later here, which we'll look at. So what this aliasing essentially allows us to do is to create a canonical name and an alias. So alias is what we reveal to the end users. So alias would be google.com, ibm.com. And the canonical name would be the actual name, which as you'll see is typically much longer. Right? And in fact, this is what's called a CNAME. This type of service is called a CNAME. And CNAMEs are very, very widely used in content by CDN networks as well. When you're offloading your content to someone else, the way to do that is to set up a CNAME record saying, hey, this particular domain points to some long address for Akamai, for example. And again, I'll show you a lot of examples today, in fact, and you'll be digging into all of this in your lab next week, which will exclusively focus on DNS as well. Right? So you'll actually do some hands-on stuff with DNS. Okay. The fourth thing noted here is mail server aliasing. So for example, if you look at UNSW, of course, we have the www. So we have a web server, right, that hosts the UNSW web page, but all of us also have UNSW emails, right? So again, if you think about it, we still use the same domain in a sense, right? UNSW, all our emails are, for example, mine is salil.kanere@unsw.edu.au, right? So what DNS does is it allows us to set up a special record, which is called a MX record, standing for mail server, whereby you can have the same name, but it's mapping to a mail server. So essentially you can have a web server, which uses this record, which is called a type A record, and a mail server, which is using a MX record, right, with the same name essentially. Finally, DNS also can help with the load distribution in a sense. So typically most web servers are not just hosted on a single machine. They are replicated simply to be able to handle load. Now, of course, each of those replicated web servers will have its own IP address. So what DNS will do is when you send a query say for mapping a host name to IP address, DNS will respond back typically with not just one reply, but maybe 2, 3, or maybe 4 options, right? And what DNS will actually do is it will keep rotating the order of those, say, 4 web servers. So when my machine queries, I might get server A as the first. When your machine queries, you might get server B as the first, right? So that allows, and typically when our machine gets these replies, we'll always try the first one. So your browser will always select the first one from that list. So this way, DNS can do a bit of load balancing across these multiple servers. And in fact, which is something that's tied to this is this whole notion of CDNs, which we'll revisit today. I know I covered CDN in the recorded lecture, but specifically how CDNs use DNS is something I'll revisit today, right? So again, this is something that CDN providers do is they will make use of some of these DNS records to be able to redirect your queries to servers that are relatively close to you, in a sense. If a query is going from Sydney, they'll try to redirect that query towards servers located in Sydney, right? And so on and so forth. Okay, so why should you have different servers for mail? Is it security? Okay, so I'm just talking conceptually, right? So physically, you might host your mail server program and the web server program on the same machine or on different machines. That's something that the person managing these servers has to make a decision on. But conceptually, we have a separate mail server program and we have a separate web server program, right? So we need to be able to provide the flexibility where people might want to host them on separate machines, right? So we should have separate entries for each of them, right? For example, you might want to outsource your web hosting to Cloudflare, but you might want to outsource your mail hosting to Gmail, right? So that having those separate entries allows you to sort of use this as you see fit. Would these mail servers have configurations of the packets being sent requiring a certain format? For example, emails and messages. Okay, now this has nothing to do with DNS. We've already looked at email, right? Last in that recording, you'll see I go over email and the specific protocols used there. This is simply to get the IP address of the SMTP server, right? So when I'm sending an email to someone at google.com, my mail program needs to know the IP address of the Google Mail server, right? So the mail program will send out a DNS query, figure out which will return back the IP address, and then my mail program will set up a TCP connection and transfer the email, right? So this process of getting the mapping happens before the actual email gets sent, and it has nothing to do with the format of the email or anything like that. Are mail servers different than web servers because of the application type? I mean, so again, remember here I'm talking of conceptually a server program, right? So of course, a mail server program is different from a web server program. They're servicing different things. Now, whether you host it on the same machine or different machines, as I said, that's something that you need to decide. And in any case, we cannot make assumptions that they'll be hosted on the same machine, right? So it's important that we have separate records for A, which is the web server, and MX, which is the mail server. Okay, so why no centralized DNS? Well, I think the reason should be apparent to you already. Of course, if you have one central DNS server, what if that fails? Then the entire internet is down, right? So we clearly can't have just one single entity managing DNS. It would be catastrophic if we do that. This single server would not even be able to keep up with the traffic volume. I mean, I don't know how many DNS queries are sent out every day. It probably goes into billions or trillions, right? So obviously you can't have a single entity managing that. The other issue is, of course, okay, if you want something single, where do you keep it? I mean, the internet is global. You can't just assume the internet is just in the US, so you can't locate it in the US and so on and so forth. And of course, it's very hard to maintain. So bottom line, yeah, just having one server doesn't scale, right? So we need something that's distributed. So let's dig a little deeper now. What are the goals here? Well, firstly, we want to be able to very easily assign domain names, and there should be no conflict, right? So two individuals should not be able to choose the same domain name. That would create a lot of problems on the internet, right? So we need a way to resolve conflicts very quickly, right? Scalable. Of course, there are many names. Essentially, it should be very easy to just create names. And you should be able to have various different kinds of names. Essentially, we should never run out of names. And it should be fairly straightforward to update these names. As I said, if you decide to change your mapping, it should be very easy to do if you wanted to do so. The other goal is, of course, it should be completely decentralized or distributed, and the entities who are administering the networks should have complete control over the domain names that they are responsible for. So for example, if I'm managing my own domains DNS, I should be very easily able to update my entries, and I needn't have to worry about the mappings for all the other domains in the world, right? I just care about my mapping. I take care of that, and every entity does the same. So that makes it very easy and scalable, right? So we don't have to track everyone else's updates. It should, of course, be highly available. So anytime you need a mapping, you should be able to request it, and you should be able to get a response as quickly as possible. Lookup should be very fast, because remember, this is just one thing. I mean, this happens before your application actually starts, in a sense, right? So before, let's say you type in a URL in your browser. Now, before your browser can actually send a GET request, an HTTP GET request, it needs to know the IP address where it should be sending this to. So the DNS query has to happen even before your browser sets up a TCP connection, right? So this is like just one part of the application, essentially. It's just the starting point, right? So these lookups need to happen really fast, because if DNS lookups take minutes, then applications, I mean, no, people will stop using applications, right? They'll get fed up. So these lookups have to happen as quickly as possible. So the way DNS tackles all this is by having all sorts of hierarchies. So there are three aspects to this. So the first, and they are in a way, there is some interconnection between them, as you'll see. So the first one is the namespace itself. So the naming conventions used for the domains, they themselves are hierarchical rather than just a flat namespace. The second aspect is how do we who administers the namespace itself. So that itself, that also is hierarchical as opposed to centralized. And finally, the actual hierarchy of the physical servers and how this information is actually stored across these servers, that is also distributed and hierarchical as opposed to centralized. So we'll look at each of these aspects in the next few slides. So starting off with the namespace itself, right? So if you think of any name, like, I mean, here, let's look at this example, right? So at the top, there is something called the root. Now the root is essentially the last dot. And this is something we don't even, I mean, if I told you there's actually a www.google.com followed by a final dot, you'll kind of start wondering, is there that final dot? Well, strictly speaking, there is, right? I mean, of course, we don't type it because your browser kind of assumes it. But strictly speaking, if you're looking up any, so Dig is a program it's essentially a command line program that sends a DNS query. So this is something you'll be using extensively in your lab. And in fact, I'll show you a lot of examples, right? So if I say this, now if you look at the question, I'll go over all this again much later in more depth in the course. But if you look at the official domain name, right here, so there's this last dot at the end, and this exists for all domains. Oh, sorry, where's my slide? Yeah, so that's essentially the root. That's the last dot in any domain. Okay. Below that, we have what are referred to as the top level domains. So these are the well-known domains that you all know: edu, com, gov, mil, org, net. Of course, this is not an exhaustive list. There are a lot more that you can find. And in fact, recently they have expanded this and created many more TLDs than there were before, right? And then you have the country ones, like here we have .au and so on and so forth. So these are what's referred to one level below. So these are the top level domains. And then below that, you have a variable hierarchy, right? So for example, here you see Berkeley, right? So that's a university, so it's under edu, right? So you could have www.berkeley.edu, but then within Berkeley, you could also have other domains, right? So say the electrical engineering and computer science department there would have their own domain, and say there's another server that's hosting something, maybe some instrumentation lab there. So that's instr.eecs.berkeley.edu.root, right? So the names essentially go up, leaf to the root, right? So this would be, as it says here, in inst.eecs.berkeley.edu, right? Now, of course, you might ask, how deep can you go? Well, you can go up to 128, but clearly that's not realistic. You'll probably go 4-5 steps deep for most domains, right? Now, the beauty of this is the collisions are trivially avoided, right? Because as you'll see later, the way this is managed is Berkeley will manage everything under here, right? So when Berkeley assigns these domain names, it will obviously know what domains it is assigning. So if it's assigned EECS, then obviously it shouldn't assign another EECS, because that would make no sense, right? And of course, EDU knows there's a Berkeley. So obviously EDU should not assign another Berkeley, right? So this makes it very easy to avoid name collisions in the first place, right? Okay, let me take some questions. So with EECS instrumental, do you mean slash? Well, I think this answers your question, right? So this is how you denote the domains. There's no slash, it's all dots. Which DNS server specifically with my network using? Is it the one by my ISP? Let me defer this question. You're essentially asking a question about your local DNS server, and I haven't yet talked about the local DNS server. So please hold on, I'll get to that in the next few slides. And yes, as the answer says, it actually depends on your settings, right? But we'll come to that. Just hold on to your questions. Okay, so this is the hierarchical namespace itself. Now the administration of these names. So this is, again, each of these namespaces are essentially, they're managed by a certain administrative authority, and then it's up to the administrative authority on how they break up the domains that are assigned to them, right? So for example, here you see Berkeley, right? Whoever is managing the Berkeley name servers is also managing this particular domain. However, the computer science department, since we are geeks, we say, hey, we want to manage our own domain. So you'll notice the main Berkeley admins, they are not managing EECS. There's a separate, what's called a zone created for EECS. And then the EECS IT guys will be responsible for managing everything under EECS, right? So this is something you do when you set up these domains. You say, okay, this is what's essentially the zone that me as an administrator will be managing. If I need to delegate some of this to someone else, I say, okay, I create another zone. Everything under EECS will be managed by those folks, and so on and so forth, right? So as it says on the slide, UCB will control everything .berkeley.edu, everything.sims.berkeley.edu. However, everything that's .ecs will be controlled by EECS, right? Whoever manages EECS. So that's how we set up these administrative zones essentially, right? And what we mean by managing is essentially this entity will be responsible for managing what's called the authoritative name server. So I haven't yet introduced what this is, so I'll come to that in a few minutes, but that's what we mean by administration. Okay. Next is the hierarchy of the actual servers themselves, right? So right at the top, we have what are called root servers. So these are like the godfathers essentially, right? So they are the big guys. They're always online. Their locations are hardwired into other servers. So these are essentially, if you don't know who to contact, you go to the root servers, essentially. That's how DNS works. Again, I'll go into all this hierarchy in much more detail, right? Remember, this entire lecture is on DNS, right? So we'll keep uncovering all of this in much more detail. Next below is what are referred to as the top level domain servers, right? So I had this slide earlier. Yeah, so each of these is referred to as a top level domain. So there'll be a separate server that manages EDU, another server. I mean, in reality, this will not be one single server, again, for the sake of redundancy, but just conceptually, let's just say there's one entity that's managing EDU, another entity that's managing .com, and so on and so forth, right? So these are what are referred to as the top level domain servers. Now, all of these are managed professionally. There's a lot of security around all of these, right? Because these are essentially the backbone of DNS. If any of this comes down, DNS breaks, right? So it's extremely important that these are kept running all the time, right? So there's a huge amount of redundancy involved here. There's a lot of security measures in place. These days, it's virtually impossible to bring down any of this. In the olden days, yes, attackers were able to do this. These days, it's virtually impossible. And then right at the bottom is what are referred to as the authoritative DNS servers. So these are the servers that have the actual mappings. So these have the actual answers. None of these servers will have the authoritative answers. These are only meant for redirecting you to the correct authoritative DNS server. The actual mapping of any query has to be answered by the authoritative DNS server, right? So this is essentially Yoda. They have all the answers, okay? They store the mappings and they are managed by the corresponding authoritative administrative authority, right? So for example, going back here to the slide before, right? So we said EECS will be managing this domains, right? So the EECS admin, they'll set up a name server, which would be called the authoritative name server. And this authoritative name server would have the mappings for all the domains under this. So for INSTR, for anything else that you could define here, right? The mappings for all those domains will be stored in this authoritative DNS server. Okay, so each server, as you saw, it stores a small amount of the total DNS database, right? So no one has the entire sort of mappings, all the mappings in the world. There is no single server that has this. As we said, the authoritative DNS servers will always store the mappings for all domains that they're responsible for. So that's essentially there. You can imagine pages of the parts and bits of the yellow pages are stored in these authoritative DNS servers. And the rest of the hierarchy is simply trying to point you to the correct authoritative DNS server, right? So this is done, the indirection is, I mean, this pointing to the right and authoritative name server starts with the root server, then you go to the top level domain server, and then the top level server will direct you further down, right? So I'll start off with a very simple example. And again, we'll uncover this as we go through this slide. So let's say my machine is called Titanium. I'm connected here in the I'm connected at CSE, right? So I'm at CSE.un. I mean, this doesn't matter where I am. I'm just showing you essentially in this hierarchy where I am. And let's say I'll come back to the local name server in a bit, but let's just assume that whenever any query, DNS query goes out from my machine, it should go to this local name server. So essentially this local name server is like a proxy. It handles all DNS queries for anyone connected to the CSE network, right? And let's say I'm trying to resolve this particular domain. So what I'm after is robot.cs.washington.edu, and of course the final dot. Okay, so I'm trying to access this particular web page, let's just say, right? So I send out a query saying, hey, I want a mapping for robot.cs.washington.edu. So what does my local name server do? So let's assume my local name server has not cached any of this. Again, as we'll move through this, you'll see that all these mappings can be cached for obvious reasons, because you don't want to repeat the queries if you already have the answer. But let's just say there's nothing in the local cache. So what does the local name server do? Who does it contact, right? It doesn't know who it should go to, who has the authoritative name server. So the safest bet is, to start off with the root, right? So if you don't know anything, you go to the root and say, hey, I mean, of course, I'm verbalizing this. This is actually a message that has a specific format, which I'll show you later, but let me just verbalize to make this a little more clear. So I'll ask the root name server, hey, do you know robot.cs.washington.edu? Do you have the IP address? The root server will never have the IP address for anything, because clearly that's not the role of the root server. The role of the root server is simply to direct you to the appropriate top level domain server. So what does the root server do? It looks at this last domain here, whatever is included. It sees, okay, this is edu, so I should redirect you to edu, right? So the reply that will come back will say, hey, go and talk to the edu TLD server. This is the name of that server. This is the IP address, right? So that's what the root name server will do. Then the local name server will go and talk to the edu top level domain server and say, hey, do you have the mapping for robot.cs.washington.edu? Now, of course, the edu TLD server will also not have this mapping, because that's not the responsibility of the edu server. However, it has an entry for washington.edu, right? So whatever x.y. It knows where washington.edu is. So it will say, hey, I don't have this mapping. Why don't you go and talk to the Washington name server? It's very likely that this server would have the mapping. So again, the reply that comes back will contain the name server for washington.edu and the IP address. So then your local name server can go and talk to this washington.edu whatever name server. Now let's just say in this case, this name server actually is managing the entire namespace here, right? So Washington actually has the mapping for this, so it will come back with the IP address and we are done, right? Now in some instances, this name server may not have the actual mapping. In that case, it may redirect you again further down. So for example, if the computer science department was managing its own subdomain here, this would come back saying, hey, talk to the authoritative name server for computer science. And then you would, this local server would query that, and then you would get the response, right? So the number of queries here can vary a bit depending on how the specific domain is managed. But this is a very good illustration of how things actually happen, right? You start with the root if you don't know anything. You then go to the TLD, then you go to this domain relevant to that particular domain you're querying, and maybe one or two steps down as well, and so on and so forth. Okay, so let's dig a bit deeper. So we'll start off in the hierarchy with the root name servers. So there are 13 root name servers. They are labeled A to M. They all have fixed IP addresses. So where is it? right? So these are the fixed IP addresses for all these name servers, right? And they go from A to M. Now, these are the original operators who were responsible for this. So VeriSign, for example, was manages A, and so on and so forth. Now, in practice, of course, these are not just 13 physical servers. Each of them has been replicated many times, and there are various replicas distributed all around the world, right? So, for example, when you're trying to contact the A root server, your query, you'll use that specific IP address, but the query will get directed to the replica of A that is closest to you. So this works on a principle called anycasting. You don't need to worry about this essentially. The idea is very simple. The network delivers this DNS query to the closest replica, right? So I'll show you a map now. This map has so this shows you all the replicas, around the world. So let's zoom into Australia. So you'll notice there are 3 replicas of L, there's F, and so on here. There's more here, and so on and so forth. So these are actually physically in Australia, right? So you see we have various options here, closer. So is this designed so that future root servers can be added? No, I mean, we are not going to add. The number of root servers is fixed and has been since day one. There are only 13 root servers. You could always create more replicas, and that's what people have been doing, right? They've been, as the load keeps increasing, they keep replicating this and getting them as close to the end users as possible, right? There's a question, can I specific root server for querying on my computer, like 888? Okay, so I guess what you're asking is whether you can use specific DNS servers as your local DNS server. So the answer is yes, and I'll talk again a bit more about this in the next few slides. So remember, I haven't even yet gone into the local DNS server yet, right? So I'll come to that. Okay, so those are the root servers. And as you saw in that example, anytime you want to start the query process, you can safely start with the root servers. One below that are the TLD servers. So these are responsible for all these .com, .org, .net, and the country-specific domains. And these are also professionally managed. These are also replicated, not again just on a single host, and so on and so forth, right? So for example, EDU cause manages .edu, network solutions manages .com, and so on and so forth. And then at the very bottom are the authoritative DNS servers. So this is actually the responsibility of the entity that is the authority for the namespace, right? So for example, if I set up my website, let's say salilkhanare.net, then it's my responsibility to manage the mappings, right? So I'm the authority. I have to set up my authoritative DNS servers, and those authoritative DNS servers should have entries for the type A record. If I want to provide email, say services, I would have to set up a MX record. Now, you could set up your own servers, like actual servers, and manage them, or you could, of course, offload this to a service provider. So for example, Cloudflare is happy to manage your DNS records if you pay them a fee, and various other providers do that. So those are the options you have, right? Whether you manage it yourself or you outsource it for a payment, right? But in any case, someone has to do this, right? Someone has to have the answers, the actual mappings for all your records. So now let's come to the point some of you have been asking, essentially the local DNS server. Now, this is not strictly in that hierarchy, as you saw there, but this is an entity that takes over the querying process essentially for all us end users, right? So each ISP will have a default name server. This is also often called a DNS resolver. If you look up on Google, sometimes you'll see this term DNS resolver used. But as the name suggests, this is simply an entity that will handle your queries for you, right? Now you might say, okay, how does my machine know who this local DNS server is? Now, in the olden days, you could configure this. I mean, you could probably still can by manually going into this file, but a plug and play way to do this, is through the DH. So when you start your computer the first time and connect to a network, your computer acquires an IP address through a process called DHCP, which we'll look at a little later. And while it's obtaining this IP address, it also obtains the information for your local DNS servers, right? So when you connect to Uniwide for the first time ever, when you're getting an IP address from the DHCP server of Uniwide, it also provides you with the DNS servers that are set up here on campus, right? And that way your machine knows that, hey, this is the local DNS server for UNSW. So anytime any application on my machine sends a query, a DNS query, it gets sent to this local DNS server, right? Now, this is normally done through an API. So there's a Unix system call called get host by name, which is triggered to, which can be triggered to generate this DNS request. So for example, when I showed you that dig example, right, that generates this sort of query that gets sent out to the local DNS server. Okay? So the local DNS server essentially is like a web. I mean, if you remember web caches, right, when we talked about our web proxies, they kind of, when you send a HTTP query, it gets sent to the proxy. And then what does the proxy do? Well, it checks if it has already cached the web page. If not, it goes and gets it from the origin server. So a local DNS server does exactly the same thing. It will maintain a cache of all the recent name to address translations. When it sees a query, it checks its cache. If it finds a mapping, it will respond right away. If it doesn't find a mapping, it will then send out a DNS query according to those steps that I showed you earlier, right? So that's the advantage of having this local DNS server, that it can do this caching and it can take care of the querying for the end machines. Okay. So there's just one entity here that's managing this. Now, as some of you asked earlier, you're not, I mean, it really depends on how your ISP has set up things, but most ISPs will allow you to use other DNS resolvers. So if you, for whatever reason, you're unhappy with your own ISP's DNS resolver, you might say, hey, I want to use some other DNS resolver, right? So for example, Google offers a public DNS resolver running on 8.8.8.8. So if you do choose so, you can configure your machine to use Google's DNS resolver or Cloudflare's DNS resolver, which is 1.1.1.1, right? And there could be various reasons you might want to do that. I'll talk a bit more about this when I talk about censorship a little later, right? But that's a choice you can make, assuming your ISP allows it. Some ISPs may disallow and may force you to use their local DNS server, right? Okay, so let's again walk through an example. So I went through this earlier, but let me revisit it because I know DNS can be a little tricky to understand. That's why I'm going slow and I'm trying to sort of revise some of these concepts, okay? So let's say I'm logged into one of our servers here, let's say Wagner, okay? And let's say this is my local DNS server, okay? And let's say I'm trying to obtain a mapping for some web server, gaia.cs.umass.edu, right? So what happens? Well, my host, let's say I've opened my browser, typed this URL in, right? My machine, the browser here will generate a DNS query, a call to get host by name essentially, which gets sent to my local DNS server. Now let's assume for the sake of this discussion, the local DNS server has not cached anything, okay? Let's say the cache is empty or it doesn't, or at least it doesn't have this mapping, right? Okay. So where does it start? Well, if it doesn't know anything, as we said, you always start with the root. So it sends a query to the root server. Hey, do you have a mapping for this? The root server will not have a mapping. As we say, the root server never has mappings for any domains. It will always redirect you to the correct TLD. So it will say, hey, this is a .edu. So you go and talk to the .edu TLD. So this number 3 that comes back, this will actually contain the name of this name server. It will also typically contain the IP address of this server. So then your local DNS server can send out a DNS query to this machine saying, hey, do you have a mapping for gaia.cs.umass? Now, of course, the TLD will not have this specific mapping, but it sees that this is a umass.edu and it knows it has a mapping, it has an entry for the authoritative name server for UMass. So it will say, hey, go and talk to UMass, the DNS server for umass.edu. Let's just say it's called dns.umass.edu. So this reply that comes back, number 5, will have the name, which is dns.umass.edu, and very likely also the IP address for this. So then your local DNS server can go there and ask, hey, do you have this mapping? Now let's just say it has the mapping. You get the mapping, and then your local DNS server responds back, hey, here's your mapping. And now you can go and set up your TCP connection and get the web page. Now you'll notice all of this, the way this works is using a concept called iterative queries, right? So each time you saw that the contacted server redirected you somewhere else, right? So the response that came back here was, hey, I don't know, you go and talk to the TLD server. Here it was, hey, I don't know, you go and talk to the TLD server and so on, the authoritative server and so on and so forth, right? So these are what are referred to as iterative queries. There's another option which is called recursive queries. So the way recursive queries would work is as shown here, right? So again, the same mapping that I'm trying to get, my local DNS server would ask the root DNS server. Now this time, notice the difference, right? So the root DNS server is not redirecting my local DNS server. Instead, it's saying, hey, hold on, I'll go and ask the TLD server. Okay, so you see number 3, the query goes here. The TLD server now says, hey, hold on, I don't have the mapping. Let me go and ask the authoritative DNS server. Now the authoritative DNS server for UMass has the mapping, so it will send back the response here. The TLD server will say, hey, okay, I got back this response. Who asked me the query? Well, it was the root server. So let me send the query back, the response back. The root server will say, hey, who asked me this query? It was the CSE local DNS server. So let me send the response back, and so on and so forth. So here you see that you're offloading the load onto another server. So this is what's called recursive queries, right? Now think about it. This recursive process is not ideal because it's putting a lot of load on the contacted name server, right? Because remember, the root DNS server is going to be queried by millions or billions of hosts, right? So clearly having the root DNS server, remember who's sending queries and then doing the querying for them and then relaying back the messages, this just doesn't scale, right? So the root DNS servers will never support recursive queries. In fact, even the TLD servers will never support recursive queries. In fact, recursive queries are hardly really supported, just for this very reason. The only recursive query that's really happening is this first one, which even if you go back to the previous slide, you'll notice this first step here is still recursive, right? Because you're asking the local DNS server to do the querying for you, and then you get back the response. So this first query is typically always recursive. The rest of the queries are typically always iterative, right? Simply because recursive queries create a lot more load on the various DNS servers. Okay, so let me take a break here. Let me quickly go through the feed first, if there are questions. So there's a question if host wants IP address for login .csc.unsw, will it query the root? So by host, I mean you're meaning some external host. Yes. So, I mean, again, maybe hold on to that question because there's caching that's happening. And as you'll see, because of some of this caching, you don't typically have to start with the root. But assuming you don't know anything, you always start with the root, right? That's like the default. So anytime you don't have any information about where to start, your local DNS server can always start off with the root. Okay. Is the local, if local DNS server is far away from the root, if so, what about the propagation delay? So yes, of course, there will be propagation delays, but as you'll see in the next slide, typically you don't even have to go to the root. Okay, so just hold on to that. So this step can actually be avoided in most cases, and you can directly start with the TLD. Okay. So mostly we use iterative requests. Yes, most of these servers will not support recursive queries because it just puts too much load on them. Why don't we cache the address of some lower level DNS servers? Yes, we do. And in fact, that's where I've taken a break. If you see the next slide, I'm going to talk about caching. What if the DNS IP is changed? But yeah, so I mean, sometimes the mappings can change and you might get a stale entry through the caching. Sometimes it's just bad luck, you have to retry. But typically, you don't make changes in a haphazard manner. So in fact, I'll show you a slide later where there's a certain process to plan these changes so that these sort of stale records do not remain in the internet, right? So there is a proper process. If you follow that process, typically you'll never encounter those kind of errors where some stale information is stored. Okay, so I think we've covered the questions. We're a little over an hour. So let's take a 3-4 minute break. So have a bit of a stretch, have a quick walk around, take a toilet break or whatever, and I'll come back in about 4-5 minutes. So let me just pause the recording for now. Okay, and I'll quickly jump out of my room. See you in a bit. Okay, we are recording again. Any further questions? No. Okay, so yeah, some questions were already hinting about caching. And this is kind of makes sense, right? Because some of this information could be cached. So anytime a name server actually learns a mapping, it will typically cache this mapping. And in fact, each DNS entry will have what's referred to as a time to live. So that indicates how long this entry should be kept by any name server, right? So the first obvious thing to cache is the top level domain servers, right? Because if you look back to any of these slides, you'll see that these TLD servers are typically well known. So almost all local DNS servers will sort of cache these TLD entries, right? So let's say you have set up a fresh local DNS server and there's someone on your network who asks for a .com domain for the first time. So your local DNS server would go to the root server. It would obtain information about the .com TLD. And from that point on, this information could now be cached. So any further .com queries, you don't have to go to the root, right? You can directly go to the .com TLD. Similarly for edu, similarly for org.au, any top level domain, right? So obviously it makes sense to cache all the TLD information. So that avoids having to go to the root each time, right? Similarly, if there are a lot of people querying, say, for Netflix or whatever, right? So one of these popular web servers, then the first time you would go through that entire resolution process, but then all the final answer could actually be stored. So next time when someone asks for Google or Netflix or whatever, you can serve them the IP address right from the cache. Now, of course, as one of you hinted, well, what if the information is outdated, right? What if the actual provider changes the web server or whatever, the actual IP address, they decide to host it on a different machine. So yes, sometimes you might have a wrong information, and that might result in a failed TCP connection setup. It's not catastrophic. Yeah, I mean, you get a wrong IP address, you try to set up a TCP connection, it fails, and then that would result in a fresh query being sent out. Of course, it adds to the delay, but as I hinted a little later, you'll see that typically you don't sort of randomly decide to change an IP address. It's a much more planned process, right? So you know in advance that you're going to change your server hardware, you want to change an IP address, so you can actually plan for these changes. And I'll show you the sort of guidelines that are typically used in one of the slides later. Sometimes these local DNS caches also store some of these negative caching. So often, right, people type in wrong addresses, right? So sometimes people by haste type in like cnn.com with 2 M's or CNN with 3 N's, right? Now, the first time someone types this will actually result in a DNS query being sent out. Of course, the local DNS server is not reading this to see if there are typos, right? But then this will not result in a resolution. The DNS query for this will never get a response back, right? So eventually the DNS query will fail. Now your local DNS server can actually keep this. It can keep information about these failed attempts, right? So when in the future, when someone types in this same thing, it will just say, hey, this is a failed, this domain doesn't exist essentially. So then it doesn't have to go through that long process, because for a query to fail, your local DNS server will try several times, right? Because it doesn't know that this is a wrong domain, right? So it's good to remember essentially what hasn't worked. That's what negative caching is, and most local DNS servers will do this. Now, how do the DNS records actually look like? So this is the format that's used by all these records. Now, mind you, there are a lot more records than what I'm going to show you. I'm just going to show you these typical 4 records, which are kind of cover most of the stuff we've discussed. Okay. So as you see, the format is straightforward. There's a name, there's a value, there's a type, and there's a TTL. The TTL is kind of self-explanatory. That's the time for which this record is active. This is typically given in seconds. The type again is kind of it kind of indicates what type of record it is. And the name and value change depending on the type. So the type A is the most classic DNS query, the IP address, the host name to IP address mapping. So in this case, the host name is the host name, the value is the IP address, right? NS is where the name is the domain, like something like that. And then the value is the host name of the authoritative name server for this domain. So essentially, if we go back, so something like this, right? So this is actually a NS record because it's pointing you to another name server, right? This number 5 is saying, hey, the authoritative name server for UMass is this specific machine, dns.umass.edu, right? So this response 3 and response 5 essentially are type NS records, because the name is the domain and the value is the actual name of the authoritative name server. As I said earlier, typically this response the actual DNS response will also contain some additional information, which I'll show you later. And this will also contain the IP address for this name server, because having that helps. Otherwise, if you don't have this would again generate a fresh type A query, right? So you don't want an extra query to go out. So the IP address is also provided as additional information. CNAME is canonical name. So this is what I was referring to, right? So for example, if you look at IBM, it's very likely the actual web server for IBM that's hosting their web page is not internally in the way they name their host names at IBM. It's unlikely to be named this. it will typically be some weird name like this, which has some internal meaning, which need not be known to us. But for us, obviously, we refer to the IBM web page as this, not by this. So CNAME allows this sort of mapping where the name is essentially the alias that is known to the public, and then the value is what's referred to as the canonical name, the actual real name as such. Right? And as you'll see later, CNAMEs are heavily used by CDNs. So when you're offloading your hosting to a CDN, you will typically have a CNAME that points to the some weird looking name for the CDN provider. And I'll show you some examples. And MX, as I hinted earlier, is where the value is the name of the mail server, right? So this would be the, for example, if the name was unsw.edu.au, the value would be maybe smtp.unsw. I don't know the exact name. It's very likely something like that, smtp.unsw.edu.au. Now remember, DNS also defines the format of the messages, and the messages here are really queries, queries and replies, and both of them have the same format. So the format is fairly straightforward. There's a 2-byte identifier. So this is essentially each query has an ID, and then the response will have the same ID, indicating that this is a response to this query, right? There are certain flags here. We don't really need to worry about this. So these flags indicate like whether this message is a query or a reply, because they have the same format, whether recursion is desired, available, whether the reply is coming from an authoritative name server and stuff like this. Down there is kind of self-explanatory, how many questions are contained here, how many answers are contained here, how many authoritative records are contained here, and how many additional records are contained here, right? Below that, we have the questions being asked. Here we have the answers. Now, as I hinted earlier, sometimes when you get the answers, you also get some additional information which can be useful to get some context about the response. So for example, it could contain information about the authoritative name servers for whatever domain was queried. It could also contain IP addresses for some of these name servers. And in fact, I'll show you some examples in just a bit. In fact, why not just run some live examples, right? So let's say I'm trying to query, oops, where did it go? Let's use the same example. Was it ac.uk? Yeah. Right. So this generates a query, and now this what I'm getting back here is essentially the response, right? So notice here, this is some of the fields in the header. So yeah, this contains one query. So the original query is always included in the response. It contains 4 answers. So notice here, I'm trying to get the IP address for that website, right? You'll notice that I got 4 answers. So what does this mean? Well, this means that the whoever's is the Oxford web server is actually replicated at least across 4 servers. It could be even more, who knows? This reply has sent back 4 name servers, right? So this was what I was referring earlier about load balancing, right? So my query got these 4 servers in this order. Maybe if one of you queries, you might get these responses in a slightly different order, right? Because normally, whatever application generated this query will pick the first one from here and try this particular IP address first, right? So by rotating this, DNS is sort of, in a sense, providing some load balancing, right? Notice some additional information that came by. So this is telling us essentially what are the authoritative name servers for that particular host name. So these are the actual names for them. And then down here, you'll see the actual IP addresses for them as well, right? Now you might ask, what is 4As? So this is IPv6. We'll talk about IPv4, IPv6 a little later. But when you see an entry like this, which has a slightly different format, this is an IPv6 address. That's all you need to know for now. Okay. And down here, you'll see some additional information. So this is actually the local DNS server on the UNSW network that did the query for me, for my machine. Okay. So this is the IP address of that. Now, in fact, I could also do this. I can walk you through that same process that we saw earlier, right? So we said, okay, we'll start off with the root. So what was it? A.root servers.net, right? So here what I'm doing is I'm specifically querying the A-root server. So I'm saying, hey, A-root server, do you have a mapping for this, right? So in that example, remember I showed you, I start off with the root. So what does the root server give me? It doesn't give me an answer as was expected, because the root server will never have the mapping for oxford.ac. But what it has given me is these name servers, right? So it has seen that this is a .uk domain. So it's pointed me to a bunch of TLDs, .uk TLDs, right? You'll notice that here. And then these are the IP addresses for those TLDs, right? So this is that response in the slides. Yeah, this one, this number 3 is essentially that what I just showed you, okay? And then you could actually follow this path if you wanted to. So you could say, hey, pick one of these, right? So let's say NSA Nick. And again, now you'll notice the TLD for UK will not have this mapping. So I never got an actual answer, but what I got was authoritative information for the ac.uk domain, right? So AC is essentially all the academic. So all the universities in UK are under this. So then I could go to one of these guys and say, hey, do you have the mapping for this? And this time I do get the answers, right? So I've actually walked you through that whole process that I showed you in the example, right? So in your lab, you'll be doing a lot of exercises with Dig, and hopefully that helps you understand some of these nuances. Yeah, I think I'll leave it at that. I need to make sure I cover the content as well. Yeah. Okay, so now let me ask you a question. So let's say you've come up with a brilliant startup. Let's say you want to call it with Network Utopia. So you want to set up a domain, networkutopia.com. Now, since it's a .com domain, you need to go to the entity that manages .com and say, hey, I want this domain. They'll say, okay, you can have it. What you now need to do, and let's say you decide to manage your own authoritative name servers, right? So let's say you want to call your authoritative name server, which in this case is, let's say dns1.networkutopia.com, right? So what you now need to do is you need to tell the .com TLD that, hey, if anyone queries for my domain, you need to redirect to dns1.networkutopia.com. So what you're doing is you're inserting two of these RRs in the .com TLD. So this is the first of those RRs, which is essentially the name server. So you're saying this particular domain, this is the name server, right? So if anyone queries for this domain, you send them to this DNS server. So this is a NS entry. And at the same time, you also need to provide the IP address, because just providing the name is not enough, right? Because remember, in the end, whoever is querying this name server needs to send the query to an IP address, not the actual name. So you also have to provide a type A record, which is the IP address of the machine that's hosting this DNS server, right? Okay, so you set this up with .com. Now you've created your own type A record. So this is the type A record for your actual web server. And let's say you also want to set up email addresses, right? So you want to give your people who work for your company addresses like salil@networkutopia.com. So that requires you to set up a type MX record for the mail server. So my question to you is, where exactly do you insert this type A and type MX record? So can you answer that? I forgot to set up a Zeetings for this. So if you could just type in your answers in the chat. So where exactly do I store the type A and type MX record? There's a question, what does RR stand for? Resource record, right? Okay, primary and secondary, I'll come to that on the next slide. Don't worry about that for the moment. Can you actually I think you're answering correctly, but a more correct answer would be, maybe one of you can give it more specific answer, let me just say. So it of course is going to be the authoritative name server that's managing the records for you, but you can actually see the name of this name server there, right? If you look at the screen, oops. I already gave you the name for it, this one. So that is my authoritative DNS server, right? That's managing all the authoritative records for me. So all the authoritative records, which are the type A and type MX records, should go and sit in this server, right? So the answer should really, more specific answer I was expecting was the actual name, which I had given you here. So dns1.networkutopia.com would actually contain this mapping. Now here it says primary and secondary. So almost always you don't want to just rely on one server, right? So what if your authoritative names, what if DNS1 went down? Well, that would mean no one in the world could actually get the mappings for your type A record and type MX record, right? So the normal convention is to always have two, a primary and a secondary, right? So you would set up something called DNS1 and maybe another one called DNS2. In fact, in that example, you saw that most real organizations set up multiple, right? Where was that? You saw there in that Oxford example, there were like 4 that I got. Maybe there were more. I just got back 4 answers, right? Okay, so let's push forward. So earlier I talked about updating DNS records, right? And I told you how this is usually a planned process. Now remember that let's say you're going to change your hardware, you're going to change your server, you're going to host your web server on a different IP. Now again, this is a planned process. And typically, you know that all the old mappings will be cached everywhere for whatever time was specified in the TTL. Now, typically, these TTLs can be like 1 day or something like that, right? And let's say you want to plan this, right? You want to plan this change. So what you do is you look at the current TTL value. Let's say the current TTL value is 1 day, which means you know that any queries out there will be at least cached for a day. So what you do is you first change this current TTL value to a very low value, say 30 seconds, right? So which means from now on, after you made this change, any further requests will only be cached for 30 seconds, right? Then what do? You wait for that original TTL period, right? So you wait for a whole day. And by doing so, you're getting rid of all the earlier records which have been cached before you made this change, right? And as we said, that old TTL value was a day, right? So you wait for a day, and in that whole day, all the caches in the local DNS servers all around the world who have accessed your domain will get purged out. Then you update the record, right? Because remember, since that past whole day, all the future mappings are only being cached for 30 seconds, right? So after that day, you can then update the record, wait for a little bit of time just for everything to settle, and then you can change the TTL back to whatever your previous time was. So in that example, I said a day. So you can now go back to a day, right? So this is a typical rule of thumb that most network administrators will use. When you have a planned change. Of course, if it's an unplanned change, then you can't really do much about it. If your server really breaks down and you have to change something hastily, then of course this doesn't apply, right? Okay, what else? Yeah, reliability. So as I already entered, almost always all DNS servers are replicated. The authoritative name servers, at least you should have 2, ideally even more, right? And the good thing with replication is then you can do this load balancing that I mentioned earlier. Now, what does DNS use? Does it use TCP or does it use UDP? Typically, the general convention is to use UDP, or at least was, till some of the new changes that have come about, which I'll talk about at the end. But for the sake of our discussion, we'll just assume DNS uses UDP, right? Now, of course, you might say, okay, if that's the case, what if a DNS query gets lost? Well, it's not so much of a big deal, right? If a query gets lost, your local DNS server can simply try again. So the logic being going through the whole process of setting up TCP connections, particularly when you have to go through several of these servers, is kind of too wasteful. It creates a lot of load on these servers and it creates extra delays because setting up connections takes up time, right? So that's the reason DNS prefers to use UDP, because it's a very simple request response operation, right? Yeah, I think we can move forward. So this is something which I've already hinted, so I'll quickly move through this. So yeah, DNS inherently provides indirection, right? So which means if you really wanted to, you could easily change the IP address, the actual machines on which you're hosting any of your servers, be it your mail servers, be it your web servers. It's fairly straightforward to do that. You don't need to change the actual domain names. So this is a very good thing that DNS provides. It also allows us to map to multiple addresses. Again, I showed you examples of load balancing. It also allows you to host many kinds of servers using the same domain names, right? So like you could have your mail servers with UNSW, you could have FTP servers with the same domain name, you could have web servers with the same domain name. So it gives you a lot of flexibility, right? Okay, so let me now move to CDNs a little bit. So this is a example that's showing you how CDNs actually use DNS. So what have I done here? I've queried for the www.mit.edu domain. And if you look at the answers there, what do I see, right? So here, unlike Oxford, where you saw I was getting just this, I'm getting something different here, right? So this is, if you just look at this, the names here that I used, it already tells you this is managed by a CDN, because Akamai is one of the leading CDN providers, right? And the way MIT has offloaded this is by inserting these CNAME records, right? So you'll notice here, by using this CNAME record, essentially, all this content is now hosted by Akamai, and here you see some of the name servers of Akamai and their IP addresses. So how exactly does this work? So let me walk you through this example. Here I'm using video content, but really even just basic web pages can be hosted this way. It doesn't have to be video. So let's look at this a bit deeper, right? So let's say I'm Bob, I'm trying to access a particular movie. I go to the main website of this streaming provider, let's call it netcinema.com, and I say, hey, I want to watch this movie, and I click, right? So what does this generate? So this, if you recall the recorded lecture, it sends you this manifest list, right, with all the chunks of the various video, the video file that you're watching, and then the streaming player on my machine will request for a particular chunk, let's say, right? So let's say it's now trying to resolve this particular URL that contains the chunk. This, of course, gets taken care of my local DNS server. Now, initially, my local DNS server will look at this and say, okay, I'm trying to access something.netcinema.com. And let's say, for the sake of this discussion, my local server has actually cached this information. So someone on this same network was also accessing NetCinema. So then it can go to the NetCinema authoritative server and say, hey, do you have the IP address that contains this particular video chunk? Now, NetCinema has actually offloaded all its content to a CDN provider. Let's just say king.cdn. So what NetCinema will do is it will respond back with a CNAME, like you saw there, and that CNAME will point to this particular CDN. Now, of course, these are all made up names, by the way. Okay. So let's say here it's saying, okay, go and talk to this particular, go and check this domain, this king CDN A11 whatever domain. So what does my local DNS server now do? It will now query the authoritative DNS server for king CDN. Let's again, for the sake of discussion, assume my local DNS server knows the authoritative DNS server for king CDN. If it didn't, it would have to go through that whole process, right? Maybe go to the root or whatever, right? Or go to .com at the very least, right? But let's just disregard that. Let's just say it knows the authoritative DNS server. So it could now go and directly ask this authoritative DNS server, hey, can you give me the IP address for the server that's hosting this particular content? Now, what the authoritative DNS server for this CDN will do is it will see where Bob's query is coming from, right? So what it will do is it will check Bob's local DNS server's IP address and say, okay, this, remember these IP addresses have meaning, right? So this IP address will actually reveal roughly where Bob is located. So for example of this discussion, let's say Bob is in Sydney. So the King CDN authoritative name server will now reply back with maybe one or two IP addresses of their CDN servers that are closest to Bob, essentially closer to Sydney or something like that, right? And then Bob will go and get the actual chunk from that server, right? Now, if Bob was somewhere else, let's say Bob was in China, in that instance, the authoritative DNS server would have replied back with a different IP address, which is very likely servers that are located in China, and so on and so forth. So what the CDNs are doing is essentially they are using this DNS ecosystem to redirect these queries to the closest servers that are hosting their content. This is exactly what Netflix and all Amazon Prime, everyone does this essentially, right? All CDN providers are leveraging DNS for these redirections. Okay. Are there any questions? No questions. Okay. Okay, I know someone is eventually going to ask me this, so I just added this particular slide. Someone is going to ask me, hey, what about dub versus non-dub, right? For example, these are, again, this is made up. I don't know if such a website actually exists or not, but let's just say www.metalhead.com or metalhead.com, right? So which should you use essentially for your, when you're setting up your host names? Should you go with a www host name or should you go with metalhead.com? Now, strictly speaking, you can go with either. Now, ideally, but from a search engine point of view, right? Because in the end, it's, can you please mute whoever happened to turn on? Okay, let me just mute all. Okay. Okay. Yeah. So from a search engine point of view, right? if you're not careful, they're going to consider, from a search engine point of view, these are actually two different domains. Oh, sorry, where was that? Yeah, right. And technically, you could choose either and redirect from one to the other. So you could, for example, say this is your main domain, and then set up a CNAME that redirects metalhead.com to this, or you could do vice versa. Technically, it doesn't matter. There are those certain guiding principles. So these non-www domains are referred to as what are called naked domains or apex domains, right? So you, as I said, you could technically serve either, and then you could just redirect, for example, using an HTTP 301 redirect message to the primary. But there are generally, people consider, the general advice is to use a www domain because they have two main advantages. So the first one being that if you look at how DNS works, it always requires that all the apex domains should always point to a type A record. So which means, let's say my domain is metalhead.com. So if I were to set up a type A record for this naked domain, it can only point to type A, right? And if you want to set up a CNAME record, it cannot coexist with any other RR type, which means essentially for a naked domain, you can only have a type A. You cannot have a CNAME, right? So that can create a problem because unlike that, when you're setting up www domains, because what that essentially means is if you set up this as your primary domain, you won't be able to offload it to a CDN provider in the future. This might not be an issue if you're going to manage your own hosting forever, but very likely at some future point in time, if your domain becomes popular, you might consider to offload it to a CDN provider. So in those instances, having gone with a www would be a better choice, because by doing so, you can do something like I showed you earlier what MIT has done, right? So they've essentially set up this CNAME, which allows them to offload their primary domain to a CDN provider. Okay. So that just makes it easier. Now, of course, mind you, you can still go with a non-www domain, and some CDN providers have workarounds for setting this up, but that's getting a bit off tangent, and that's not something we need to worry about in this course, right? There's another issue associated with cookies. Again, this is not super important. I won't be asking you exam questions on any of this. This is just for your own knowledge. But essentially, cookies of all the Apex domains are also automatically passed on to any subdomains. And doing so can essentially slow down your, because having unnecessary cookies will hurt your browsing performance for the users. And there's also a security issue. So if you're really interested to dig this up, certainly check this website. This goes into a lot more detail about this whole issue of www versus non-www. Again, I won't ask you any of this from this slide on the exam. This is just for your information. Now, what about the reverse? So DNS also does a reverse thing. So far we've been saying, okay, I want to go from a domain name to an IP address. Now, there are certain reasons why you might want to do the reverse, and DNS has a way to do this. This is what's referred to as a PTR record. Now, you might ask why you might want to do this. So in fact, traceroute and ping, right? When you ran traceroute, you saw that you were actually getting names for those IP addresses. How was that possible? Well, that's possible through reverse DNS. If you look at some of your SMTP email headers, you'll see that if you look at all the received header fields, you'll see there's a actual, the names of the mail servers are also provided, not just the IP addresses. So that's again done using reverse queries. Various forums, they track users. So they look at the IP address of the users from where they log in, and from that they get information of the actual domains these users are connecting from, just to get some extra information about them. And then various logging and monitoring tools also make use of that. And as I indicated earlier, the CDN providers also use this to figure out where you're from. So when they see your IP, they try to figure out where you're located, which domain you're coming from. So these reverse queries also have some use. What else? Well, there's this issue of trust, which I kind of hinted, right? So we say, okay, within an organization, you typically use the organization's DNS, local DNS server. Well, what if this organization is trying to censor you? So it is very easy to do that through DNS, because anytime, say, this organization wants to censor certain web pages, all they have to do is do not reply back with the mappings for any DNS queries for those blocked websites. That's very easy to set up. A very simple rule that you can set up in a DNS server, that any of these blocked websites do not provide mappings, right? So that is essentially censorship. And again, there's a lot of debate about this, whether or not to allow this. And if you don't want to use your local DNS server, then you could try to use some of the public DNS servers. Now, if your local ISP really wants to be super restrictive, they could actually block any DNS queries going to some of these locally available DNS servers, and that effectively will give you no choice, right? But if they don't, you at least have a choice. So you don't necessarily have to use your own organization's DNS server. You can use some of these publicly available ones as well. There's a query: are proxies used to overwrite DNS servers? I'm not sure I quite understand what you mean by that question. What proxy are you referring to, and what do you mean by overwrite? So as I said, you can choose your local DNS server, right? So when you get your IP address, your local DHCP server will give you your local DNS server. If you do not want to use it, you can go into your computer, depending on which OS you use. There are ways to configure alternate local DNS servers. So if you don't want to use your ISP's given DNS server, you might choose to use, say, Google's DNS server, right? So that is possible, certainly. Okay, where are we? Time. So a few more minutes left. So I'll talk a bit about attacks here. I hinted earlier that in the olden days, people were targeting some of these root DNS servers or TLD servers by just sending them too much queries than they can handle. These days, this is not possible because all these servers are replicated. They've got a lot of security around them and so on and so forth. Given that DNS by default is inherently insecure, there are all sorts of attacks that could be possible. Like, for example, someone could set up a fake local DNS server on your network, and when they see a query being sent out, they could intercept that query and send back a response, right? So things like that, these are much harder to do these days because, again, there's mechanisms to prevent this. I'll show you one interesting example. So of course, I also mentioned this earlier, that if you can bring down some aspects of the DNS ecosystem, it does cripple the internet. So still there are certain things that these attackers try to exploit. Now, I won't go into all those details here, but you can certainly look up this website and search on Google for some recent attacks that have been launched on the DNS ecosystem. So from time to time, you do see some of these attacks come up, and they certainly can cripple the internet, or certain parts of the internet, to be more precise. So let me just elaborate a little bit on one of these attacks. So this is what's referred to as a cache poisoning attack. So let's say I'm a bad guy, or let's say you are a bad guy, one of you, and let's say you control the name server for drevil.com. So let's say you have set up a domain, Dr. Evil, right? And you have set up your own name server. And let's say you ask someone on the internet to visit your website, right? So let's say maybe me, right? So I type in your website, www.drevil.com. Now this will result in a DNS query being sent to your authoritative DNS server, which is managing the drevil.com domain. And the response I get, let's just say it looks something like this, right? So I get back a type A record, which is the web server that's hosting your website. This is fine. I also get some additional information in the authority section. So what is it? Well, it's the name server for the authoritative name server that's managing your domain. So let's say that's DNS1. Okay. So this is also fine. But here is the problem. What is this second record? So this second record should ideally be the secondary DNS authoritative DNS server, right? So ideally this should be dns2.drevil.com. But what do we see here? Well, I see a strange entry saying the second name server for Dr. Evil is called google.com, right? And then down here, you see again something strange. You see an additional section. Now, normally this should contain the IP address for DNS1 and DNS2. But what do we have here? We've got an IP address for google.com, right? And this is a problem because what this is doing is it's essentially creating an entry for google.com with this specific IP address, which is not a google.com machine, but it's something that's managed by this evil person itself, right? Now, why might this person be doing this? Well, the reason this person is doing is that some of this information, we said that all of this is getting cached, right? So my local DNS server now has cached all of this information. So it has even cached this incorrect record for google.com. Now, what this means is if anyone on my network tries to resolve google.com, my local DNS server may actually feed it this incorrect information, right? Which is clearly not the correct IP address for google.com. So this is what's referred to as a cache poisoning, where by poisoning here, we mean feeding in incorrect information, right? And then what this attacker could do is they could set up a web page that looks exactly like google.com here. And then they can do all sorts of, they can essentially find out what you're searching for on Google, right? And things like that. So that's the malicious intent. Now you might say, okay, if this is possible, then clearly we have a problem. Well, these sort of attacks are no longer possible. And the reason being, in this case, my local DNS server is never going to cache entries like this. It will certainly cache this one because that is the authoritative DNS server for this domain, but it will not cache these two because these are not authoritative, right? Dr. Evil has no connection with google.com. And this information that's being sent is not coming from the authoritative Google name server. It's coming from the Dr. Evil name server. So my local DNS server today will never cache these entries. It will only cache this one here and this one, right? So these sort of cache poisoning attacks are no longer possible, right? So this was just an illustration of how things you could have attacked in the past. Now, DNS security is certainly improving. There's all these security extensions. Again, this will not be on the exam. These are just some things you might explore if you're interested. So certainly there are security standards in place now to avoid some of these problems. And in fact, there are two very recent new introductions whereby you can actually send DNS queries over HTTP and over TCP. So these are very fresh new standards being adopted. These are slowly being rolled out. In fact, a lot of browsers these days will support DNS over HTTP queries. So in these instances, the DNS query will not happen over UDP like we looked at before, but rather over HTTPS. Okay, so that makes it much more secure. Now, again, none of this will be on the exam. This is just in case you want to explore this a little further by yourself. So certainly look this up if you're interested, but I won't be asking you questions on this. So let's just take a couple of questions and then let's end this. Or maybe what I'll do is, since we are getting to the end of the hour, maybe let's leave this here. We'll start our next lecture by going through these quizzes. So that will help you sort of refresh some of these concepts. Okay. So let's end the recording for today. I'll stick around for a couple of minutes if you have any questions. If not, have a wonderful week. And I'll see you all on Monday. And yeah, just make sure you start working on the second lab, which is already out there. Yeah, we'll look at the question later. I don't want to answer this question now. Okay, have a wonderful evening. Yeah, this was meant to be a joke. The first answer obviously is a joke. Okay, bye-bye everyone. I'll stop the recording now.